Hi, let's start. I'm Rafail, and today we're going to talk about PyTorch. It will be an introductory tutorial, though we'll also cover some more advanced things that you might not be familiar with. So before we start, a little bit of history. Originally, deep learning was developed in academia, and most frameworks were developed in the universities. For example, originally Torch was developed in NYU, Rafail in UC Berkeley, and Theano in Montreal. And later, when it became more popular, some big corporations acquired those frameworks and merged them. And Torch and Caffe became a basis for PyTorch, and it was acquired by Facebook. Now it's Meta. And Theano became a basis for TensorFlow. Of course, there are many more deep learning frameworks, but we'll focus on PyTorch, and all the homeworks will be in PyTorch, and you'll probably do your final project in PyTorch. So yeah, that's what we're going to talk about. So why learning PyTorch? By the way, if you have any questions, you can just stop me at whatever time, and also ask questions, I guess, on Zoom, if you can hear me. I hope.
These layers are not open source as well?
What?
These libraries are not open source?
Layers?
Libraries.
Libraries. Most of them are open source. Yeah, so PyTorch is open source, TensorFlow, like, yes. So most of them are open source. So why learn PyTorch? First of all, as all deep learning frameworks, it implements many necessary modules for deep learning. As you'll see, and maybe understand yourself when you work with PyTorch, it is very suitable for quick prototyping. It's easy to debug your code, and it's really Pythonic. You really feel like you're writing just like a Python program when you're dealing with PyTorch, unlike some other deep learning models. And yes.
What do you mean by quick prototyping?
Just like you don't have, like, maybe you'll see it later when we'll discuss like computation graph and stuff like that, but you just write code and it can be executed without like first defining how your code will run and then like putting the data in. So it's very nice in that sense. You can just play with it very easily. Great. So today we'll cover mainly three things. First, tensors, basic operations, and vectorization. Then we'll cover PyTorch modules, and then module and how to use them to build architectures and like neural networks modules. And we'll also cover automatic differentiation, and we'll understand how PyTorch helps us to automatically calculate gradients for all the parameters in our model. Cool. Let's start with tensor. So when I say tensor, in this tutorial, it's just a multi-dimensional array. It's nothing more. And we'll use torch tensor to represent mostly anything, inputs and outputs of our model, weights and gradients. And it is just like NumPy array. I'll do a lot of comparisons to NumPy, and you'll see it's very, very similar, at least in that sense. So for example, to create a torch tensor, you can create from a list of lists or like from whatever Python structure you have. And by calling torch.tensor of data, you'll get the torch tensor. Or you can also create a tensor from NumPy array by calling torch.fromNumPy. So tensor has several attributes. First of all, it's its shape, and it represents the number of dimensions and how many elements in each dimension there are. Its data type. So in this case, X data is int64, it's an integer. And there's also a device. So usually the device in CPU by default, but as you'll see later, we can also transfer it on GPU on our video card, and it will be much more efficient to work on GPU than on CPU. Let's start with some basic operations. So first, let's define two tensors, like one, just a 1 through 9, and another one is an identity matrix. And let's see what we can do with them. You can define element-wise addition just by doing A plus B, and you can see it's indeed an element-wise addition, just like in NumPy. Subtraction, element-wise multiplication, division, and you can also exponentiate, so A to the power of B. So each element of A is in the power of each element of B. And of course, a very useful operation is matrix multiplication. And in PyTorch, it's earliest with an add sign. There's also a function, but this is more convenient to just write A add B, and this is multiplying two matrices. And yeah, cool. So there are also in-place operations, which will be useful, I guess, in all your homework. And it's just like in NumPy or just pure Python. When you just do A plus B, the value of A, of course, it does not change. You can see that A stays the same. But you can write A plus equals B, and it will in place change the values inside the tensor A. Subtract it, and there are many other in-place operations. And there are a lot of like other operations that will not cover that are very basic in PyTorch. For example, like this, one of these examples is clamp, also probably useful in your homework, where when you want to clamp the values of tensor in between two ranges. And what I wanted to show here is that many operations have not in place and in place counterparts. So as you can see here, when you just write a.clamp, the value of a does not change, but there is also an operation with underscore after it, which changes the value in place. So in many operations, if you see underscore, this is just like a convention to put underscore for the function that operates in place. Good. Good. Indexing, yes.
Can you go back one slide? Is there a difference between doing A plus B to A equal A plus B?
Again, you mean A plus equals B and A equals A plus B?
Yes.
I think there is some difference, but like for you, it will not be, it will be the same. I mean, maybe in low level code, maybe there is a difference, but for you, no difference. So you can do A equals A plus B or A plus equals B. Cool. Indexing and slicing is done exactly like in NumPy. So you can take like individual elements. You can take rows and columns or even for different dimensions. So for example, here, it will turn a first row and the first column of tensors A and B. And when you do this slicing, one thing to note is that you'll not preserve shape this way. So both of the slices will be of the same shape, with just like 1D tensor. Cool. You can also do concatenation, splitting, stacking just in NumPy. For example, you can write torch cat of A and B, which is concatenation, and it will concatenate two tensors. And indeed, it produces a shape of 6 by 3 when we concatenate two tensors of size 3 by 3. And in many operations, there is a keyword dim, and this replaces, if you're familiar with NumPy, it replaces axis, and it can specify on which dimension do you apply this operation. So for example, here we can concatenate two tensors along a different dimension. So before we concatenated by default on dimension 0, and now we can concatenate on dimension 1, and we can concatenate it horizontally. Nice. Also, reshaping, just like NumPy, if the original shape is 3 by 3, you can reshape to whatever tensor size, okay, not whatever, such that the product of elements in each dimension stay the same. For example, if the original tensor is 3 by 3, you can reshape it to 1 by 9 or 9 by 1. Very useful. Another operation that is will be useful for your homework is squeezing and unsqueezing. So this operation adds a like redundant dimension if you want inside your tensor. For example, here you can add the dimension just before the original 3 by 3, and the output tensor will be of size 1 by 3 by 3. And there is also a squeeze operation that removes this dimension.
But why?
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 For example, if you want to like, for example, sometimes you want to add like a batch dimension. For example, you have a tensor of size like 3 by h by w or c by w, and you want to pass it to the model. Usually, models like that you build accept like in the form of batch size by channel by h by w. And with this operation of unsqueezing, we can add 1 at the beginning, and it will be of size 1 by C by H by W, which the model will accept. This is just like, gives you more control over your tensors.
It doesn't look like you're passing what the size of the extra dimension should be.
Yeah, so on squeeze just adds always 1. It's like an empty. It just adds like an extra bracket. You can write just like a list, and of one element we can add another bracket. That's what unsqueeze does. Great. So what we discussed before was basic PyTorch operations, and let's now discuss how we can utilize the GPUs in our deep learning adventure. So,
Sorry, so
yes.
unsqueeze would turn, for example, a row vector into a column vector?
Like if you had a tensor of shape 3, just like then unsqueezing in the dimension 0, as shown here, will turn it into tensor of shape 1 by 3, but you can also unsqueeze at the dimension 1, and then it will turn into a tensor of shape 3 by 1. So you can unsqueeze before and after, and it will turn either to a row vector or a column vector. Yes?
You unsqueeze on multiple dimensions, or you have to unsqueeze multiple times?
You have to unsqueeze multiple times. Yeah, that's annoying. Yes, about GPUs. As you'll see a bit later, GPUs are very useful in deep learning, and we do most of our operations on GPU because it will be much faster. So why? Many operations in deep learning, usually matrix multiplication, can be parallelized. Like each small multiplication in matrix multiplication operation can be done in parallel, and GPUs are very good for this because they have multiple small cores that can perform these operations in parallel. So, for example, this is an image of some GPU, and each green cell there is a small core that can execute operations in parallel. So that will be very useful because we have a lot of matrix multiplications in deep learning. So in PyTorch, it's very easy to transfer between CPU and GPU. So first you need to check if you have GPU available. If PyTorch that you installed sees the GPU, you write torch CUDA is available, and if it returns true, then GPU is available. If it's false, then you did something wrong, and PyTorch does not see your GPU. You can get how many devices do you have, how many GPUs do you have, usually it's just 1. And to transfer a tensor from CPU to GPU, you just call this method tensor.toDevice. So currently device is called CUDA. This is a name for device that will transfer to GPU. So as you see before, the device of tensor X data was CPU, and after we called to CUDA, it became GPU. This is clear? Yes.
If the GPU doesn't work on CUDA?
I think you can install PyTorch versions not for CUDA, for like AMD video cards, but I've never tried this. Like 2 years ago, it had limited support. Now I think it's better, but yes, I've never tried this. Yes.
I think it's like I use a M1 back, and you can just do MPS for the front shaders, and it just works the same way.
Yeah, so CUDA, I guess, is just like the name of the device that you want to transfer it. So usually it's NVIDIA GPU which uses CUDA, but if you have Mac or AMD, it'll probably be different. If you'll be using Google Colapse, I think it's just transferring to CUDA. Cool. So let's see some case study why we want to use GPUs, and let's see how long does it take to multiply two matrices of size 1000 by 1000. So we can do it first for using for loops over rows and columns. Then we can multiply like matrix for each row of another matrix. We can multiply two matrices with PyTorch on CPU. And we can do the same, but before we transfer all of the tensors to GPU. And do you want to guess how much time did it take to multiply matrices of 1000 by 1000 for case 1 when we had nested loops? Like approximately.
1 second.
1 second. How many?
No, 1 millisecond.
No, actually it was 20 seconds almost. On CPU, it's on CPU. It's two for loops. It's fine. It will be much better. For this case, it was 132 milliseconds on CPU, when we do vectorized operations, it was 25.8 milliseconds. And when we transfer it to GPUs, do you want to guess? If not, 1 millisecond, almost half a millisecond. So as you can see, doing operations on GPU is much more efficient, like orders of magnitude faster than doing it on CPU and writing your own for loops. So like takeaway message is, don't implement it yourself if you don't have to. Just use vectorized built-in operations from PyTorch and use GPU resources when possible, because it will be much more efficient and it will save you a lot of time. Cool. So there are a lot of operations, as I said, and all of them are vectorized, like multiplication, summation, subtraction, and so on. We will not cover all of them. Also linear algebra operations, such as matrix multiplication. So with this add notation, you can multiply, for example, a vector by matrix, or here's actually a matrix by vector, two matrices of different sizes, and of course, very useful, a batch matrix multiplication, where we have two batches of matrices. Like first batch is B by N by K shape, another one is B by K by M, and with the same add notation, with the same matrix multiplication from PyTorch, we can multiply the corresponding matrices between two batches. Another very useful tip is to use broadcasting when available. For example, in many cases, fully matching the dimensions between two tensors may be redundant. For example, when you want to add to a matrix a row or a column, as here you have a matrix of size n by m, and you want to add to each row another vector. You don't have to actually repeat your vector b multiple times. PyTorch will do it for you. You can just write a plus b, and it will work. Of course, it also works for different dimensions, not just for the dimension 0. Also, broadcasting will work when you will try to multiply the batch of matrices with a single matrix. So it will multiply each element, each matrix in the batch with a given matrix. Very useful. You'll probably use it in your homework. Cool. So far, probably most of you knew this stuff or were familiar from NumPy, but now we're going to a little bit more advanced operations that you will certainly use in your homework 3, I think, or 2. And first will be a torch einsam. And this is an implementation of Einstein summation convention. So, and this implements a lot of operations on tensors, and I will explain what it does just now. So let's say an example, we want to multiply a matrix by a vector. So you can use torch einsam to do this. And it accepts two different things. First, the operands, the things that you're going to apply this on. In this case, it's a matrix and a vector. And another thing is a summation scheme. And the summation scheme is a string where for each operand, for each dimension, you assign a specific letter. So for example, in this case, the matrix, you assign for rows letter I, and for columns, you assign letter J. And for vector, you assign vector letter J. And then what you do is you multiply over dimensions with the same letter. You see J is matching in matrix and vector. And in the output, after the arrow, you sum over the dimensions which letters are not in the output. So in this case, it's I for rows, J for columns, and also J for vector. So J matches with J in the vector. You multiply element-wise, and then you sum over J since J is not the output. Very useful. So of course, you can do much more complex things with this torch einsam. For example, this batch matrix multiplication, as we saw, is possible with simple add notation, but einsam can also do this. And a nice thing about torch einsam is that if you have a formula like this with indices, where you just write down what the specific element of the output tensor should be, you can convert it very easily to torch einsam, to this Einstein summation convention. And let's say you have two batches of matrices, and we can just convert the formula that we have to this summation scheme. You can see B and K, B, K, M, and the output is B and M. And this is very, very useful, and you probably also use it in your homework. Yes.
So the advantage of this method is that I don't have to transpose and
Yes, yes, you can just like match the letters. So for example, this formula, you probably won't be able to do this with just simple matrix multiplication in PyTorch, but with einsum, it will be very easy once you have it. Once you write down all the indices, it's very easy to convert. Like you have summation over different dimensions, you have multi-dimensional tensors, so usually it's very hard to perform, but it's very easily transferable to this Torch einsum. And it's very fast, it runs on GPU, and I recommend using it when you need it.
What does it mean there that you're getting K in the output and J in the output if you're summing over?
So this, like the output is a three-dimensional tensor, and we just reference each dimension with different letters. So like just like index the dimension, first dimension is I, second is J, and third one is K in the output. And this is just like an example formula.
You're not summing over K and
No,
J in this case.
no, we're just summing over L and M. Okay.
You said at the beginning, like the torch sensor can contain not only numbers, it can contain any data structure.
We'll use it to represent different data structures, but usually it's like it's integer or real or even like complex number, but it's just a number.
I'm just thinking impossible to use that for mathematical objects, like derivations. Do you for derivations?
Probably not. This operation is implemented, I guess, only for some specific data types, like real, integer, and complex. But this framework, this Einstein summation, is a general thing. It exists not only in PyTorch, it also exists in NumPy and many other frameworks. So, general thing. Next operation, which is a bit more advanced, is a gather operation. And it samples elements from a tensor according to an index. So this is a nice visualization that I have here. Is let's say we have a multi-dimensional tensor, like three-dimensional one, with channels, like 4 channels and H by W. And we want to sample from this tensor. Actually, when I say sample in this case, it's not probabilistic. It's just like indexing, taking elements from the tensor according to some index. So for each spatial location here, the element in the index represents from which channel do we want to draw an element. So here we want to draw from from channel 0, from channel 0, from channel 1, and channel 3. And gather allows us to perform operations that are not possible with the simple indexing that I showed you before. So let's see how it's implemented in PyTorch. So first you define the dimension over which you perform this gather operation. And let's say you have some source tensor that you want to sample from of size like 4 by 4 by 6, as in our example. And you define a index, and each element of index, as I said, shows like the spatial location, sorry, not spatial, like the channel in this example, where you want to sample from. And implementing it in like for loops, it's very easy. You define the output tensor, and you can do it like in for loops for channel, for H, for W, and you just populate the output tensor. But again, doing for loops is very inefficient. So what you can do is just call one line of this torch gather, and the inputs are the source tensor, the dimension over which you're sampling, and the index, which is like the tensor that shows from where to sample. I really encourage you to play with it yourself, because it will be much more clear when you perform it yourself. But it's a very useful operation. You'll certainly, I know for sure that you'll use it in your home. So better to know this.
Can you explain again what's the source thing?
Yeah, so maybe it's better just to look at this image. You have source here is the colorful tensor on the left. You see, like we have 4 channels in this example and like H by W. So it's like a 3-dimensional tensor in this case, like C by H by W. And index just tells you from where to draw this element. So for each spatial location, you see the index H and W matches the tensor on the left, H and W. You're just sampling according to the index. So here's from channel 0, from channel 0, channel 1, channel 3, and so on. Does this help?
Do you get the same location, but you write there which channel?
Yeah, when I say channel, I mean like some, yes. In this case, it's a channel, right? It's like C by H by W, but you can perform gather on different dimensions as well. But yes, index tells you from which spatial location to pick.
Your index always has to have exactly the same shape as your source matrix, except for the
Yes.
the dimensionality.
Yes.
Broadcasting on this?
I don't know if it's like, if this is called broadcasting, but yes, like the elements inside the index should be like, you see here, it's the elements of index are from 0 to 3, including, because we have only like 4 channels. So it's 0, 1, 2, 3.
So can you gather, for example, with a matrix of just one column and get all the rest of the columns that gather automatically to the same?
I'm not sure. I have to play with it. I don't know. Great. So there's also an inverse operation of gather. So if gather is sampling a tensor according to an index, there is also a scatter operation that does the opposite. So given a sample tensor and the index, it spreads it back. So here it's a sample tensor as we just had from gather operation. And given the index, the same as before, gather just adds the values from the source index to the output for a specific spatial location. So here you define the output shape. Yes, you have a question?
Yes, short question and practical question. I mean, usually you are doing pre-process with the channels and register them and align them. Do you see really a practical place where you use it, like different indexes from different?
Gather for sure. I used it several times in my work. Scatter, I don't think that I use it. I don't remember using it, but it's useful, just not for my work. But in the homework, you'll probably use scatter when you implement the backward operation for some functions. You'll probably use scatter add. So gather is certainly practical, and just a tip how to know when you need gather, when you're just sitting for 15 minutes trying to make sense of your indexing and you can't make it with just default indexing in PyTorch, then use gather. It will probably work. That's how I use gather. Whenever I'm stuck with indexing, then I remember how to use gather. Cool. So about scatter, again, this is a backward operation. It's instead of sampling, it scatters. It spreads the given tensor according to the index. So this is an in-place operation. So first you define this tensor on the right.
Rafi?
Yes.
Could you re-explain the intuition about why gather helps you make sense of your indexing?
I mean, this was more like a joke when you're stuck with indexing that you can't do with a simple operation and PyTorch, when you can just like do take the first and second and third element, like then you use gather whenever you're stuck. That's it. Nothing more. Just helps you perform more complex operations on tensors, like more complex indexing. That's it.
Thank you.
Yes.
So then would the other indexes of the output be 0?
The other elements
So like
that you don't add with the scatter operations that are not changed, they stay the same. So scatter is an in-place operation. Let's say you have some tensor on the right, which is already predefined. Like let's say it was a 0. All the elements were 0. And then you add to this tensor, to some specific locations, the elements from the source on the left. Yes? I understand it might be too much for this tutorial, so yes, I really encourage you to play with it yourself. Play with gather, with scatter, with ensemble and stuff like that. Maybe I will even skip the more detailed explanation of scatter. I just say that you do scatter add like this, like one line in the bottom. That's how you do scatter. Play with it. That will be very nice. Okay, one hard part over. We discussed some PyTorch operations, and now let's see how we can actually build a model using PyTorch. So usually the general scheme that we'll be using is the following. You have some input, you have a model, you pass the data through the model in the forward pass, you get some output, you have some supervision signal, and you calculate the loss between your output and the supervision, and then you do a backward pass to update the weights of the model. So let's first discuss how to actually build the model. And to do that, we'll use PyTorch submodule NN, which stands for neural networks, .module. And this is a class in PyTorch, and you will use it whenever you want to create your own class of models. You create a class that inherits from this class. So first, you also need to define an init method in this class where you will store all the parameters of your model, like the trainable parameters and whatever other information that will be used later. And you'll also define the forward pass, which defines exactly how the data will flow through the model. So in this case, let's see, we build a simple MLP. We define a class MLP, which inherits from an n.module, as you can see. Don't forget the line where you call the initialization of this NN model, this super.init. Then in the init method of MLP, you define all the trainable parameters, all the fully connected layers, the activations and stuff like that. And then you also define the forward method, where you actually define how the input, in that case X, will flow through the model. It's very simple to do in PyTorch. So after you define this class, you create an object of this class. Here you just call MLP. And yeah, you're ready to go. You can just pass input through the model and you'll get some output, which is very nice. Any questions on this? Yes.
Do you use all the operations in the GPU, or do you specify only the metrics interpretation for the GPU?
So
Is there any advantage to use some of the CPU and GPU?
no, whenever you can do it on GPU. And to run your code on GPU, you have to also transfer your model to GPU, as you can see in the bottom right. You need to call model.toCUDA, or whatever device that you have, and it will transfer all the parameters of your model to GPU, so it will be compatible with your input data, which will also be on GPU. Yes.
Does the flatten function, I understand it's like inherited from models, right?
Yeah, there are a lot of built-in functions.
So what does it do to it eats any X?
It just like reshapes whatever tensor that it encounters with a 1D tensor. If you have some like B by C by H by W tensor, it will reshape it to a tensor of size B times A, C times H times W. Yes. Another quick tip: if your model is very simple and just contains a list of modules that that are supposed to be called one after another, you don't actually have to define a class. You can just call this sequential model, which is also from NN submodule from Torch. You can call this NN sequential and input there all the submodules that you're going to be using. So here you can see, instead of defining init and the forward, you can just put your submodules there and just call it the same. Great. So far we saw two parts: how to build a model in PyTorch and how to perform a forward pass, how to actually do some predictions. Let's now discuss how we're going to update the parameters of the model. This is happening in the backward pass, and luckily for us, PyTorch got us covered. It is implemented already in PyTorch, but we're still going to dive deeper in how exactly PyTorch does this, because in the second homework, you'll be doing it yourself. We will not rely on PyTorch. So let's see how PyTorch actually computes the derivatives automatically. And a small reminder example why we need to compute derivatives and find gradients with respect to parameters of the model. So let's say we have a toy linear regression example. We have an input x and output y. Both are just numbers. Your hypothesis is a linear predictor where you just multiply x by some parameter w that is going to be updated. Your prediction is y hat. And then your loss is a squared loss, where just y hat minus y squared. And as you saw before in different tutorials and lectures, we're going to update the parameter w with the gradient descent. And to do that, we need to calculate the derivative of the loss with respect to w. In this case, it's just like all of them are just numbers, but in the general sense, you'll calculate the gradients of loss with respect to parameters of the model. So to do that, PyTorch actually has additional attributes for each tensor. They are the grad attribute, where we'll actually store the gradient of this specific tensor, and a gradient function, which is a reference for a function used to obtain this tensor. And I will elaborate on this gradient function a little bit later. So let's see a small example in PyTorch. So again, linear regression, as we just discussed, have x, w, and y. Now they're tensors. And our prediction y hat is just x times w. You calculate the loss. And to calculate the gradients of L with respect to w, we call this backward method, L.backward. And what this does, it calculates the gradients for all the tensors that have this flag requires grad equals true. So after executing this code, you can actually inspect the gradient of this w parameter, and you can see that the gradient of w is -4. And for example, for x that didn't have this requires grad equals true, the gradient is still none. They're initially nuns, and only after this backward pass, they're being populated. Cool. So let's see how PyTorch actually does this. And to understand that, we'll need to understand what is a computational graph. So in high level, computational graph is a directed graph where the nodes correspond to operations that you perform or variables like x, w, and y. And it will be used to differentiate, like to find derivatives with respect to parameters using the chain rule that you learned. Yes, nice. Cool. I'm glad. So the computational graph for this, the example looks like this. You see the leaves are x, w, and y, and the operations are also represented in the graph. You can perform the forward pass on this graph just by calculating y hat, then calculating this like intermediate result a, which is y hat minus y, and then you square this a and you get the loss. This is like a forward pass of the model. And we can also find like derivatives with of L with respect to all the intermediate results. So I already pre-computed them, so I'll just go over them quickly. So dl dA is 2a, dA dy is 1, dl dA, y hat is 1, dA dy is -1, dy hat dx is w, and dy hat dw is x. And you can also get the specific values for each of these derivatives by just substituting the values that we had before. Do forward pass, and then get the values for each derivative. Very easy. And you can see, as you remember, you can get the derivative of L with respect to W using the chain rule, which is just this. So like multiplication of corresponding derivatives. And you can see that these derivatives actually form a path on the graph from L to the W. So when you multiply the derivative of dl dA times dA dy hat times the dy hat dw, you get -2 times 1 times 2. This is a very simple thing to, like, this is a very simple computational graph, and in real life they're huge. So that's why you get -4. Is this thing clear? Yes. Great. So there are actually two types of dynamic graph in deep learning frameworks. There are static and dynamic graphs. So static graphs are the types of graph where you first define the structure and then you inject the data to it. And the dynamic graph is the graph where you define the structure on the fly. So for static graph, you first define the operations, like you multiply two elements, then you subtract the result with some other element, you square it and get it. You fix this graph, and only then you pass the data through. This is the static graph. And for dynamic graph, you define variables and their relations, and the graph is built implicitly when you actually execute the operation. So first you have this x, w, and y as before, and only when you execute the operation, the graph is built. So the difference between static and dynamic graph is, again, static you define and then run operation. Dynamic graph is defined by running, so it's defined in runtime. Static graph will be slightly faster because you can do some optimizations before you are actually running the code. And the dynamic graph is more flexible. You can run like your code with ifs or for loops, and it will be defined on the fly. So static graphs were used in the TensorFlow package with version before 2.0. And the dynamic graph is used in PyTorch, which is very nice. And in TensorFlow package with version bigger than 2.0. And static graphs are not convenient, at least for us. They're good when you want to optimize some like deep learning application and deploy it to some, I don't know, mobile phone or somewhere else. But if you want to quickly prototype, you want to do it probably with a framework that uses dynamic graphs. Any questions? Yes.
So does PyTorch does not have an option for static graphs?
No.
So I guess if this is training time, it's not that big of a time. When you deploy it, you can.
I mean, like PyTorch supports there is some ecosystem that helps you like deploy your already pre-trained model to some mobile devices and some other stuff. But I've never dealt with this, and I don't know how they are compiling this. So for us, what is important is that PyTorch uses dynamic graph, which allows us to have crazy forward passes. You can like in your forward pass of the model, you can add an if statement, and it will work. So, which is a huge advantage, I think, of dynamic graphs over static ones.
What is it that is static and dynamic about the graph? That you can change the graph as you go along?
Yes. So the dynamic graph, you can change it as you go, depending on like exactly what the code is executing. And in static graph, you first define exactly what operations will you perform, and you cannot change it later.
And you can change it even when it's like half-brained or something like this?
No, never. Yeah, like for static? No.
Dynamic.
For dynamic, like maybe like an intuitive example would be like if you have an if statement in your forward pass, which sometimes is true and sometimes is false. So like let's say first half of your training, like the if statement in your forward pass is true, and then the graph looks like this, and then suddenly it becomes false, and then the graph looks like this. Different. So that's like gives you more flexibility. Cool. So again, in PyTorch, the computational graph is dynamic. So it's created in the forward pass while you're like calling your model, while you're applying the model on your data. And yeah, unless you use this torch no grad, then the computational graph is not created. We'll cover it a bit later. And then this graph is deleted when you call this backward function, when you call this loss.backward, then the computational graph is deleted. So let's see again, how is it implemented in PyTorch, how this computational graph is exactly done in PyTorch on the same example of linear regression. So first, you initialize your tensors, x, w, and y. And as you can see, initially, the gradients are none because we didn't call the backward pass. Then we start the operations, and then the graph is built on the fly. First, it's just x times w, you get y hat. And when you call this operation, PyTorch actually stores the function that was used to create this tensor. So in this case, y hat was created by multiplication operation. So PyTorch stores this, and it stores it in a grad function attribute of a tensor. So if you actually look at y hat dot red function, it will show you this multiplication backward object. And this function is just a reference for what was used to create this tensor. And this is just like a derivative of y hat with respect to w. So in the forward pass, PyTorch creates this graph and stores this function. In this case, it will be derivative of y hat with respect to w, which is just x. And we actually will need to know the value of x to perform the backward pass. So it also stores the value of x aside that will get in the forward pass, in the backward pass. Sorry. I feel that it's not clear. Do you have any questions on this? I'll just go in the conditional graph a little bit more, and then we'll do the backward pass. So if you have any questions on this part for now, you can ask. Yes.
What is the bias?
Just in this model, there's no bias, just x times w. This is just our toy model. We didn't have any bias here. Yes.
So does it also store the w value that's going to for the x value?
Actually, we won't need the w value because only w requires grad equals true. If x also requires grad equals true, then it will also store the w value. But in this case, we only need to find derivatives with respect to w. That's why we need to store the value of x. Yes.
The requires grad.
Does it actually store the value or a
Yes.
reference to the? I mean, if you manually change the value after, then.
I guess you can mess with PyTorch like that, but like from PyTorch, I don't think that you can access this context variable manually.
It's memory, right?
Yeah, so I guess you can somehow like change the value of x that is stored, but
Maybe it has a version control system to check.
let's not go into this like how you can change the values of this context variable because you don't need it.
What's inside Molebeck?
Molebeck is again this like a derivative of y hat with respect to w. This is like a function, and you'll implement this like backward. You'll implement specifically this in your second homework, and maybe then you'll suddenly realize, that's what he meant.
You need to specify the requires grad equals true for every variable that you're going to want to optimize, or
Yeah, if you define the parameter manually, if you define a tensor manually like this, then you need to write requires grad equals true, and only then it will store any gradients after the backward pass.
so both for the weights and for the for the layers, the hidden layers, right?
So when you define like parameters in your model, you like call this and then dot linear, and inside this, it's already doing it by for you, like it already automatically writes requires grad equals true. But when you create a tensor from like nothing, like here, when you just define w from a list of with element 1, you need to write requires grad equals true. Okay, so this is only one operation in the forward pass when we create the conditional graph. Next is y hat minus 1. The next node is created, and let's say we call it a number an a. And when we create another thing is saved. Exactly, the gradient function of a will be subtraction backward, and this is the derivative of a with respect to y hat. So in this case, it's 1. So this is the function that will store, but we don't have to add anything to the context variable because this does not depend on the input, and in the backward pass, we will not need it. Then finally, we square a to get the loss function L, and the gradient function of L is the power backward because L was created by squaring the a, and so it's like a power of 2. And in the backward pass, we'll need to get the value of a, so we store this value of a in the context variable, and this power back function itself is the gradient of L with respect to a, which is just 2a. So now this is a forward pass done. Yes?
why didn't you need to specify the requires grad equal true for either A or Y hat?
So intermediate variables are automatically, like they automatically get requires grad equals true. If they are a product like of tensors that at some point require grad, then they will also require grad.
But the CTX, AX on the side.
Again, what is CTX?
Yeah.
CTX is like a context variable. Exactly, it's a stack where we store the values themselves. We store the value of A and X from the forward pass. So like in this case, X was 2 and A was -1. So PyTorch stores aside this these values that it will use in the backward pass, like to calculate exactly the values of the gradients. Any more questions? We are now going to the backward pass, where we're actually going to use these values.
Why is X context dependent? Because it's static.
Look, X is your input and it will change. Let's say for the next iteration of training, like for the next iteration, X will not be 2, it will be 3. It's like it's a variable, it can change. So for the backward pass, you need to know
Why not Y? Why should be also?
You don't like, if you go back, you never actually had to store the value of Y because we never calculated the derivatives with respect to Y. And yeah, here, if you go here, you need to store the value of X because we are calculating the derivative with respect to W, right, which is X. So we need to store the value of X for the future. Here, we store the derivative of A with respect to Y hat, which is always 1. It does not depend on anything, so we don't store anything. Okay? Okay. And later we square it, and we store the derivative of L with respect to A, which is 2A, and we need to store the value of A somewhere, and it doesn't. Does that answer your question?
I don't understand it.
So maybe,
Yes.
so Y and Y hat do not change, like, they never change. So we
Yeah.
just want to store them. That's the, like,
Um,
they're already,
No, and I don't think that's the correct explanation. You store only what is required for the backward pass, like depending on what you are calculating the derivatives with respect to. Like currently, you don't calculate like derivative with respect to X. So in this case, derivative of Y hat with respect to X will be W. But since you don't calculate this derivative, you don't store the value of W. So you store only X.
Well, how do you know, like if it's a dynamic graph, how would it know that it doesn't need to store it until it gets to the point where it computes the backward pass?
So like for Y hat, for example, it knows that like W, so Y hat is X times W. It knows that W requires grad equals true and X requires grad equals false. So it knows then we don't need to calculate the derivative with respect to X after performing this operation. That's it. So here, after we go like here, it knows to calculate A, Y hat requires grad equals true, and just Y requires grad equals false. So it knows not to store unnecessary things.
what would happen in the context if, say, Y requires pricing?
It will also calculate gradients with respect to Y. Like usually you don't need to, right? Like because it's your supervision, you don't want to change your supervision.
Right.
But you can. Like,
And then it will store in context also, right?
like specifically in this example, no, because you don't need to store anything because it's just like a subtraction. You see, like the derivative with respect to Y hat is 1, and derivative with respect to Y is -1. So you don't need to store anything at all. It's just like always a constant.
So it depends on the functions.
It depends on the function and whether you're calculating derivatives with respect to it or not.
So there is a very complicated algorithm how to know what to. It's not a basic algorithm how to understand what to store and what to not. Depends on the function.
Depends on the function and if variables in this function requires grad or do not require grad equals true.
What if the function is not It's not like made with just squares and.
It will always be made like this. Like computational graph, like decomposes very complicated functions into these small operations where just like multiplication, summation.
Very
So
long.
it will be a huge graph. In real life, they're very big, and they will be all decomposed in this simple operation of squaring, like multiplication and stuff like that. Cool. So this is a forward pass, and in the backward pass, we first call L dot backward, and first we calculate the derivative of L with respect to A to store the gradient of A, and this is 2A, and to get the actual value, we need to get the value from the context variable, bam, and therefore, like we know that the A dot grad is equal to -2 because we stored the value. Now it updates the gradient of A. We go further backward. Now we need to calculate the gradient of L with respect to y hat. By chain rule, it's this, dl dA times dA dy hat. We know dl dA before, it's -2, and dA dy hat is just 1. So y dot grad will be also -2. We go even further. Now we calculate the derivative of L with respect to W. By chain rule, it's this. And we know from before the derivative of L with respect to y hat. And we multiply it by derivative of y hat with respect to W. And this is 2A times 1 times x. And we get the value of x from the context variable to get the specific value. And that's why we have the W dot grad is equal -4. Is it clear at least? Like 20% clear? 20% clear. Good job. You have questions? Okay. Cool. So after the backward pass is done, the gradients are reset, and then the graph is deleted to free the memory. One funny thing to note is that you can actually, the gradients are accumulated. So if you perform forward pass and backward pass, and then again forward and backward, the gradients will be added on top of already existing ones. So after the first backward pass, the gradient of W was -4. And if I perform the forward and backward again, it will add another -4 to the gradient of W. So you can perform this multiple times, and the gradients are accumulated in the specific tensors. The hard part over. Everything else is very easy. You can also disable gradients, and this is useful when you perform validation of your data. When you don't want to create any computation graph, it will consume much less memory. It will be faster. So this is very useful. Do that when you don't want to actually update parameters. When you evaluate your model, do that. You write with torsional grad, and everything that will be inside this context, inside with torsional grad, as you can see here, will have requires grad equals false. So the computation graph will not be created. And therefore, it will be faster, less memory, and stuff like that. Another very useful thing to note is you can actually remove one specific variable from the computational graph if you don't want to pass gradients through it. So in this case, you write .detach, and it detaches the variable from the computational graph, and the gradients don't flow through this variable. So you also need to do this when you convert from tensor to NumPy. You need to call detach to remove from computational graph. Then you convert it to CPU if it wasn't already on CPU, and only then you can convert it to NumPy.
So detach just takes only the data and all the attributes it removes. Right?
Yeah, kind of.
Rafi, can you explain one more time the disable gradients? Why that would help you validate or verify a model or graph?
So it does not help you. It just makes it faster, and it makes sure that the parameters are not updated in this in the validation. Like during validation, when you want to actually measure the performance, you just want to do forward pass, and to make sure that the parameters are not updated, and to make it just faster, because the creation of computational graph takes some time and memory. You write with torsional grad, and it just makes everything requires grad equals false, so the computation graph is not created.
I see.
Cool. Yes, so we just saw how to perform one pass of forward and one pass of backward. But actually, in real life, we want to perform multiple passes, like of forward, backward, and there could be different update algorithms, and they are all stored in a submodule of Torch called Torch optimizers, and they're actually used to update parameters of the model. So let's see an example of Torch optimizer. First, it's just like, let's say you have some stochastic gradient descent, SGD, and to create this optimizer, you just call Torch optim SGD, and the parameters of this object are the model parameters, like the trainable parameters of your model, like fully connected layers, like weights, biases, whatever you have, and some hyperparameters of the algorithm itself. So in this case, it's just like learning rate, the step size. So you just write LR equals learning rate. That's how you define the optimizer. And optimizer has two main methods. They have more, but two are mostly used. Only two are mostly used. First, it's optimizer zero grad. So what this does, it zeroes out the gradients for all the parameters that this optimizer affects. So in this case, it will make all the gradients zero for all the model parameters, like for all the weights and bias. And I'll discuss a bit later why do we need to make it zero, why it will be useful. And the main method is optimizer.step. It's like a generic function for different optimizers, and it implements actually the specific update mechanism. So for this case, it's just like W minus learning rate times the derivative. So when you call this optimizer.step, it actually uses the gradients that are stored in the tensor to update this tensor. Cool. So let's now put everything together, what we just saw, and see a bit more complicated example, but it will be much easier than that computational graph part. So let's classify the fashion dataset, which contains like 10 classes of different garments. And we'll see how we create hyperparameters, how we handle data, how we create model, loss, and optimizer, how the training loops are actually performed, and we'll see everything together at the end. This is the last part, so let's continue. So first, to create the hyperparameters, it's just like learning rate, the batch size, the device that you're going to use, and this is a nice one-liner to determine which device you're going to use. And like it's CUDA if CUDA is available, otherwise it's just CPU. So these are the hyperparameters. To handle this data, we're going to use the built-in like Torch datasets. There are a lot of datasets that are already available from Torch package. You just need to call this specific function to download them. So this is like downloading the train data and the validation data that we're going to use. And just for our convenience, we're going also to use the data loader. This is just an iterator that defines the logic, how we're going to feed the model the data. Like maybe we want to shuffle it before we feed to the model. Maybe we want to feed it with like some specific batch size. So this data loader defines this logic. So like shuffle equals true, for example, makes the data shuffled, and batch size just determines the size of the batch, as the name suggests. Then you define a model. Here I use just like sequential to make my life easier. You define the loss. Since it's a classification task, it will be like cross-entropy loss. And the optimizer, we're going to use SGD. And this is the training loop. Let's go over the training loop, how exactly we are doing training loops in PyTorch. So you iterate over the batches of data that the data loader gives you. So it's like input, X, and Y is your supervision. Then you pass them both to device by calling to device both on X and on Y. You do the forward pass of the model. You get some prediction. You call your criterion, in this case, cross-entropy loss, on your prediction and the supervision. Then a very important step, you zero out the gradients of all the model parameters. we need to do this on each iteration, because if you don't do this, as you saw before, the gradients will be accumulated over different iterations, and it will be not a correct step from like a stochastic gradient descent. So usually, like in 99% of the cases, you need to call this optimizer zero grad to zero out the gradients on each iteration. And it's very often forgotten, so make sure that you have this in each iteration.
What do you mean accumulate? It's adding to this attribute, to this value?
Yeah. So remember when I showed like when you calculate the gradients with respect to W, it was -4, and then I performed the forward and backward pass again, and it added another -4 to W, and now the gradient is -8. That, like, we want to avoid that. Sometimes it's useful. That's why PyTorch does that. But in most cases, you don't want to do that. That's why you need to zero out the gradients on each training iteration. Then you actually calculate the gradients by calling loss.backward. It automatically creates gradients in each of the model parameters. And then you perform a step by calling optimizer.step, and it updates the parameters, and your model is training. Any questions on this? Cool. In inference, you just do with torsional grad, as I showed before, to make sure that the parameters are not updated, and you just do the prediction or whatever you want in the validation. It's up to you. So the overall training process you do like for different epochs. So epoch is like one epoch passed when you feed all the data from the data set to the model. Usually that's what we define by epochs. And you do training for several epochs. And inside each epoch, you do like multiple iterations. So as you can see here, there's a for loop over epochs. And before there was a for loop over the training iterations, like inside the data load. And one nice thing is that when you actually train your model, it's very useful to visualize your data, and not just data, but also like the result of training to see what's your model performance, like the accuracy or the loss or whatever else you want to track from the model. For example, here you can see that our model is overfitting, so it works much better on training data than on validation data. Cool. Yes.
Yeah, make an example of like accuracy. Like it's some we never use accuracy in the training process, right?
Yeah, you don't.
An evaluation thing.
Yeah, you just like this is like a metric that you like evaluate your performance, like how accurate your predictions are. But this is not the same as loss. Loss is like direct supervision, and accuracy is just for you. Like you're correct in like 95% of the cases. This is just okay per person.
Could it be that the structure of the accuracy plot is like principally different than the structure of the validation? Is there any additional information that you get from the accuracy plot
compared to
the loss?
Yeah, for example, your loss is meaningless, and it is decreased by but the accuracy is not increased for some reason. Like it is meaning, like if your loss is decreasing but accuracy stays the same, then it tells you that something is wrong. Maybe your loss is incorrect or something else happened unexpected. So they're usually correlated, but if they're not, that's a sign that something is wrong. Yes?
You reach overfitting, to prevent it, you need some stopping condition in the epochs.
Yeah, like there are different ways to avoid overfitting. Yes. Maybe your model is too big or something else, but yes.
So what are the ways to put stopping prediction, like just looking on the validation result and
like if your validation accuracy plateaued, maybe that's the time to stop training. Or if your training loss plateaued or like validation loss like didn't decrease for several epochs, then you can stop your training. Cool. So today we focus on PyTorch. Like specifically, we discussed tensors, how to build architectures using PyTorch, and how does automatic differentiation package work in PyTorch, but there is much more just in PyTorch itself. But additionally, there is a huge ecosystem that helps you track experiments, like visualize your data, apply transforms of images and different stuff. Like we can't cover everything in our tutorials. So I just encourage you to Google or ask me if you want, like, how can I do transformations on the images better? You can ask me, and maybe there is a library that does this for you. For example, I really recommend this INOX thing. Look into this. It will help you to transform your tensors, like reshape, like change dimensions and stuff like that, much easier than in default PyTorch. I use it like daily, all the time, and this is very useful generally. So thank you. I think next Monday there is no class because of Christmas. And next Wednesday we will be taught CNNs, convolutional neural networks. Thanks for coming.